Hello everyone, and thank you for attending today's webinar, Predicting Multi-Component Adsorption from Single Gas Isotherms using MicroActive Software with IAST. My name is Jeff Kenvin, and I'm the Vice President of Science at Micromeritics Instrument Corporation. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple engagement tools you may use. You can expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner. If you have any questions during the webcast, you can submit them through the Q&A. We'll try to answer these during the webcast, but if we run out of time, it will be answered later via email. Additional materials are available in the resource list. We encourage you to download any resources or links that you may find useful. Some networks cause slides to advance more slowly than others, so logging off your VPN is recommended. If your slides are behind, pushing F5 on your keyboard will refresh the page. If you experience any problems during the session, you can find answers to some common technical issues located in the Help Engagement tool at the bottom of your screen. An on-demand version of the webcast will be available after today's webcast and will be emailed to you once the session has concluded. I'm pleased to introduce today's speaker, Dr. Julian Hungerford. Julian joined Micromeritics in 2020 as an application scientist. Since joining Micromeritics, Julian has contributed to the development of the Micromeritics Breakthrough Analyzer, as well as the characterization of porous materials. Julian, it is an honor for me to introduce you today. We are so glad you could be here today to share your insights on predicting multi-component adsorption from single gas isotherms using MicroActive Software with IAST.
Thank you for the introduction, Jeff, and thank you for everyone attending my presentation today on an introduction to ideal adsorbed solution theory in MicroActive, predicting multi-component adsorption. Today's webinar is going to begin with an introduction to ideal adsorbed solution theory, or IAST. After that, we will collect some data and show how IAST can be used to predict multi-component adsorption behavior in binary systems using the 3-flex. Lastly, we will then conduct experiments using those same multi-component binary mixtures in a breakthrough system using the Micromeritics BTA. We will then compare our predictions that were obtained using the 3-flex with our experimental data collected using the BTA to see how well our experimental predictions match the breakthrough data. Beginning with the introduction to ideal adsorbed solution theory. Ideal adsorbed solution theory, or as it is referred to, IAST, is a technique for predicting multi-component adsorption behavior using only pure component adsorption data. This technique is extremely valuable as multi-component static adsorption instruments are very complicated to build, and as of today, no off-the-shelf models currently exist. This technique allows you to predict how multiple adsorbing species will behave using only pure component data, which is easily available and can be collected using a variety of instruments, such as the 3-flex, which we will be looking at today. The methods presented here, however, will be applicable to other instruments as well. All you need is the software features of either the 3-flex software or MicroActive to process the data and predict multi-component adsorption. IAST was originally developed by Myers and Prausnitz in 1965 and is still widely used today for predicting multi-component adsorption isotherms due to its simplicity of its use. IAST has been shown to work well for adsorption of similar molecules. An example would be hydrocarbons, such as methane and ethane. IAST predictions come with several assumptions. First, the adsorbed phase is thermodynamically ideal. In other words, there's no volume change associated with mixing multiple different gases or adsorbed species. Additionally, the equilibrium pressure for each component is simply the product of its mole fraction and the adsorbed phase, and the equilibrium pressure for the pure component at the same spreading pressure. This criteria fulfills Rault's ideal solution, in which the force of attraction between dissimilar molecules will be the same as if they were in the pure state, and the volume of the solution is the sum of the components. With these assumptions, we would expect that chemically similar molecules would adsorb as predicted by IAST, whereas chemically dissimilar molecules would deviate from our predictions. IAST was recently introduced in MicroActive and the 3-Flex software for versions 6.0 or newer. It allows users to collect pure component isotherms on their ASAP 2020, TriStar, or 3-Flex and predict multi-component adsorption. Currently, the software is compatible for binary systems only. The predictions are available for all gases in the standard Micromeritics database. This includes all of the gases that are listed on the screen. Some key gases of interest include carbon dioxide, ethane, ethylene, methane, nitrogen, oxygen, xenon, and krypton, as well as many more. If you're curious about any particular gas mixture, please contact us at support@micromeritics.com to find if that gas can be used with our IAST predictions. For today's webinar, we will be analyzing 3 microporous carbons. We will begin by collecting single component isotherms using the 3-Flex. We will be targeting the gases carbon dioxide, methane, and ethane. We will then predict multi-component behavior via IAST. Our hypothesis is that IAST will accurately predict the multi-component adsorption for methane-ethane mixtures, but fail to correctly predict carbon dioxide mixed with either methane or ethane. The reason for this goes back to the assumptions in IAST. Methane and ethane are very similar molecules, whereas carbon dioxide is very distinct compared to either methane or ethane. Following the collection of these isotherms, we will then look at multi-component adsorption using the Breakthrough Analyzer, or BTA. We will collect breakthrough curves for methane-ethane, methane-carbon dioxide, and ethane-carbon dioxide mixtures. Finally, we will compare the breakthrough data to IAST predictions that we obtained using the 3-Flex. We chose to use the 3-Flex because it's a high-performance adsorption analyzer that is capable of collecting isotherms down to 10 to the negative 9 p/p0. It is ideal for the analysis of microporous materials, and its ultra-clean manifold design features hard seal valves and chemically resistant metal seals to provide chemical compatibility, increased evacuation speed, and vacuum performance. It also has the lowest outgassing rate in the industry, which will allow us to collect the most accurate single-component adsorption isotherms, which are very important for obtaining the best predictions via IAST. For the second part of today's talk, we will use the BTA, whose superior design minimizes dead volume and delivers accurate experimental results. The system contains patented high-performance blending valves, and there's a thermostated environmental chamber provides uniform temperature control even when using vapors. This will allow us to collect our multi-component adsorption data and compare it to our IAST predictions. Next, we will look at our IAST predictions using the 3-Flex. The 3 microporous carbons that were chosen for this experiment were obtained from Supelco. They consist of carboxin 1018, carboxin 1021, and carbosieve S3. Each material was tested for single component adsorption of carbon dioxide, methane, and ethane on the 3-Flex. Then MicroActive Software was used to predict mixed gas adsorption isotherms. Starting with carboxin 1018, we can see the adsorption isotherms of methane, CO2, and ethane on the material. We can see that at 1000 millibar, carboxin adsorbs the most CO2, followed by ethane, and then weak adsorption of methane. At low pressures, we see that ethane is actually favored over carbon dioxide as well as methane. On this slide, we see the results of the IAST predictions for carboxin 1018 for methane and CO2 binary adsorption. In the left corner, we see the quantity adsorbed versus vapor phase mole fraction. In the top right corner, we see vapor phase mole fraction versus adsorbed phase mole fraction. In the bottom left, we see spreading pressure versus absolute pressure. Spreading pressure is the opposite of surface tension, such that high spreading pressure means that a molecule prefers to adsorb to the surface, or spread out on the surface of the adsorbent. whereas low spreading pressure means that the molecule prefers to interact with itself versus the surface. In the bottom right is the isotherm, which we showed earlier on the previous slide for all three components. Next, I'll go through showing all of the different predictions for carboxyl 1018 as well as the other materials, but I kind of wanted to break down the different features that are available within our software for IAST and how those look in the software. So I'll go a little bit more quickly through all the other binary mixtures and kind of highlight some of the key points. So shown here are the predictions for carboxyl 1018 for our methane, CO2, CO2, ethane, and methane, ethane. Some of the key things to point out here are that we can see that in general the spreading pressure of methane tends to be very low on the surface of our materials, such that both CO2 and ethane are favored for adsorption in our carboxyl 1018. Lastly, we can also see the selectivity at different vapor phase mole fractions for our binary mixtures. We can see here that carbon dioxide is heavily favored over methane with a selectivity between 8 and 18, depending on the vapor phase mole fraction. Carbon dioxide is slightly unfavored over ethane for adsorption with a selectivity below 1, ranging between 0.7 to 0.5. Ethane adsorption is heavily favored over methane adsorption with selectivity ranging between 30 and 40. Next, we'll move on to carboxyl 1021. Once again, in the low pressure region, we see the highly favorable adsorption of ethane, then CO2, and lastly, weak adsorption of methane. At higher pressures, the total capacity of the adsorbent for CO2 and ethane are fairly similar, but methane still lags considerably behind. Looking at the IAST predictions, we can once again see plots for composition mole fraction, spreading pressure, as well as our isotherms. Looking at the selectivities, we see a similar story here where carbon dioxide is favored over methane with a selectivity of roughly 5 regardless of vapor mole fraction. Ethane is a little bit more favored over carbon dioxide adsorption, showing selectivities of carbon dioxide to ethane between about 0.4 and 0.3. And once again, ethane is still heavily favored over methane adsorption with selectivities between about 20 and 25. Our last material is Carbocef S3, which showed similar trends to our other materials, showing favorable uptake of ethane, then CO2, and lastly, methane at both high and low pressures. Looking at our IAST predictions, we can see our composition plot, mole fraction, spreading pressure, and isotherms. This is showing a similar story here as what we've seen for our last two materials. Looking at selectivities, our carbon dioxide to methane selectivity ranged from 4 to 5. This sample showed the highest selectivity for ethane over carbon dioxide, with a carbon dioxide to ethane selectivity of about 0.2, and then once again showed very strong ethane over methane selectivity, ranging between roughly 30 and 35 across the entire vapor phase mole fraction. To conclude this part of the webinar, all samples were highly selective to ethane over methane. All samples were also selective to ethane over carbon dioxide, but the degree to which varied considerably. Carboxyl 1018 was slightly selective with a selectivity of about 1.7. Carboxyl 1021 was a little bit more selective with a selectivity of roughly 3. And then carboxyl S3 was the most selective for ethane over CO2 with a selectivity of roughly 5. So there was quite a bit of variability in the terms of the selectivities between ethane and carbon dioxide. All samples were selected for carbon dioxide over methane, with carboxyl 1018 being the most selective for CO2. Now that we've conducted these experiments and have our predicted multi-component adsorption for our mixtures of CO2 methane and ethane, we want to compare them to experimental results, and we will do this using the breakthrough adsorption. Next, we'll move on to our multi-component adsorption experiments using the BTA. We analyzed the same 3 Supelco microporous carbons, carboxyl 1018, carboxyl 1021, and carboxyl S3. Breakthrough measurements were conducted using binary mixtures of 50-50 carbon dioxide methane, carbon dioxide ethane, and methane ethane. Samples were activated in pure nitrogen. Nitrogen was used as a carrier gas, and argon was used as a tracer gas to determine the start of the breakthrough measurements. Selectivity was determined for all the 50-50 mixtures, which we could then compare to IAST predictions. Starting with carboxyl 1018 breakthrough, for our carbon dioxide methane mixture, we observed a CO2 quantity adsorbed of 13.7 centimeters cubed per gram STP and a methane adsorption of 1.06 centimeters cubed per gram STP, giving us a selectivity of CO2 to methane of 13.7. These results are in line with what we predicted based on IAST, where CO2 was favored over methane. However, the magnitude of the selectivity was slightly higher than we predicted, with a selectivity of about 13.7 in breakthrough experiments. Moving on to CO2 over ethane adsorption, 0.71 centimeters cubed per gram STP of carbon dioxide was absorbed, and a very strong adsorption of ethane was observed, reaching a capacity of 27.7 centimeters cubed per gram STP, giving us CO2 to ethane selectivity of 0.03. This followed with what we observed in IAST regarding ethane being favored over CO2. However, the selectivity was significantly in favor of ethane over CO2. Looking at our last mixture for carboxyl 1018 over ethane and methane, the methane adsorption was 8.2 centimeters cubed per gram STP, and the ethane adsorption was 32.7 centimeters cubed per gram STP, which resulted in a selectivity of 4.3 for ethane over methane. This was fairly in line with our predictions. Looking at our next material, carboxyl 1021 breakthrough, once again we saw strong adsorption of CO2, reaching a capacity of 14.5 centimeters cubed per gram STP, and methane adsorption of only 0.73 centimeters cubed per gram STP, resulting in a selectivity of carbon dioxide over methane of 20.8. For CO2 and ethane, we had a total CO2 adsorption of 6.5 centimeters cubed per gram STP and an ethane adsorption of 17.9 centimeters cubed per gram STP, resulting in a selectivity of CO2 over ethane of 0.36. Lastly, for carboxyl 1021, for ethane and methane adsorption, methane adsorbed 5 centimeters cubed per gram STP, and we saw an ethane adsorption of 23 centimeters cubed per gram STP, resulting in a selectivity of ethane over methane of 4.68. Moving on to our last material, carboxyl S3. For CO2 methane breakthrough, we saw CO2 adsorption of 17.7 centimeters cubed per gram STP and a methane adsorption of 1.9 centimeters cubed per gram STP, resulting in a selectivity of CO2 to methane of 9.9. For CO2 and ethane, we saw CO2 adsorption of very small quantity, only 0.1 centimeters cubed per gram STP adsorbed, whereas for ethane, we saw an adsorption of 31.8 centimeters cubed per gram STP. Lastly, for ethane and methane, we saw a methane adsorption of 9.1 centimeters cubed per gram STP, and ethane adsorption of 36.2 centimeters cubed per gram STP, giving us a selectivity of slightly over 4. To summarize all these breakthrough experiments, all samples were selective towards CO2 over methane, and all samples were selective towards ethane over both methane and CO2. Samples were highly selective for ethane over methane, with selectivities ranging between 4 to 5 for all samples. Samples vary drastically in their selectivities for ethane over CO2, with the lowest performing sample having a selectivity of roughly 2 for ethane over CO2, and the highest performing sample having a selectivity of roughly 100 for ethane over CO2. Another thing to point out is that all of our breakthrough curves were sharp, such that mass transfer limitations were not observed. And lastly, for all of our breakthrough experiments, we did not see any pressure drop in any of our testing. So comparing our IAST predictions and our breakthrough results, so IAST was able to predict the general trend we saw regarding which gas was more favorably adsorbed in each binary mixture. Shown on the screen, we could see that our weakest adsorbing species in all of our samples was methane. CO2 kind of performed in the middle, and then ethane was the most favorably adsorbed species across all of our samples. We did see that the magnitudes of the selectivities determined using IAST versus breakthrough measurements were fairly different across our different binary mixtures. But it was good to see that the overall trend did match with our predictions. With that, I would like to thank everyone for attending my presentation today on an introduction to ideal adsorbed solution theory in MicroActive, predicting multi-component adsorption. And I'd be happy to take any questions at this time. Thank you.
Thank you, Julian. I'm opening the chat for everyone's questions now, and we already have a few. Julian, on your IAST predictions, what options are there for models for actually fitting models to the isotherms? Because there are several approaches that people can use for IAST.
Yes, so there are several options that are available for model selection for the IAST. Some common models that you've probably used before and some less common models. So you have options such as using Langmuir model. You can use the regular Langmuir model. You can also use the dual site Langmuir model. You also have the option to use the TTE, SIPS, Toth, and Redlich-Peterson. So there's a pretty broad range of models for fitting your isotherms that are available. And you'll be able to, you can see in the isotherm screen at the bottom right when you develop those IAST predictions, you'll see your experimental data on your kind of the individual points, which are like the triangles, and then the actual isotherm, the solid line is actually the prediction. So in general, you're trying to find, which model best fits your experimental data that you collected. And there may be several models that fit reasonably well, and really that's where you have to use some of your kind of chemical intuition in terms of, how would a CO2 molecule or other adsorbing gas molecule adsorb onto your site. You know, probably the easiest way to visualize that is, you know, that some of the differences between Langmuir and dual site Langmuir. You know, if you're adsorbing some sort of molecule like hydrogen, for example, which is diatomic, you know, you may have those two different adsorption sites for hydrogen as an example.
Thank you. In the second portion of your talk, where you really focused on using breakthrough to compare it back to the IAST, some of your experimental curves had a periodic pattern associated with them. Will they influence your selectivity values in any way?
So they won't have a significant influence once saturation is reached. It could change it slightly, but in general, you know, I am trying to wait for equilibrium, you know, obviously during an experiment, because adsorption is an exothermic process, and I'm trying to, you know, control the temperature as best as I can using the system that I have. So there will be, you know, some adsorption and desorption, you know, as it's adjusting the temperature, just due to the fact that, you know, there is, you know, adsorption is an exothermic process, so it will generate some heat, which in turn will lead to a little bit of desorption of molecules, and then the system will work to correct that and get back to the set point temperature that I've set, and it will, you know, so there is, you know, a little bit of adsorption, desorption going on during an actual analysis. So it can be hard sometimes to directly compare, you know, these static adsorption isotherms, which are very, very controlled, you know, only one single component, to something like a multi-component experiment where you have gas flow, you have, you know, changes, you know, much more significant changes usually in temperature, just due to the fact that, you know, when do you actually reach equilibrium, and selecting that point can have some small influence on your quantities adsorbed. So it is you know, a lot. I guess analyzing breakthrough curves is a little bit more subjective than what it would be to analyze isotherms as an example.
Here's a really practical question associated with your presentation. Is the software intuitive, and is there help available for someone that's using it?
Yeah, so I would say that the software is very intuitive. So I didn't kind of go through step by step how to do it here, but online on our website there will be an application note that's released alongside this presentation, and there's an experimental section in there that pretty much walks you step by step on how to actually use IAST and the software. But it is, in my opinion, fairly intuitive to use. And it's part of both the 3Flex and the MicroActive software version 6.0 or newer. So you know, you can freely download that from our website in the software section, and you'd be able to do these predictions yourself using your own 3Flex data.
You presented really great data for methane, ethane, and CO2. Could someone perform really similar work with nitrogen and CO2?
Yeah, so you could do the exact same study using there's very wide variety of gases. So nitrogen and CO2 is something that you could, you know, quite easily do using, you know, any of our main physisorption instruments, TriStar, 3Flex, ASAP 2020, and then be able to get IAST predictions. So that is perfectly doable in the software.
A really practical question relating back to the materials that you selected. Do you have on hand the BET surface area values for these carboxyl materials, or approximate values?
That's a good question. I believe that I can look some of those up. I don't have them right in front of me, but I have analyzed those materials for BET surface area before. They are all highly microporous materials and have surface areas, I believe, somewhere in the 400-ish meters squared per gram range.
For these types of analyses, do you think similar studies can be performed, like the earlier question on nitrogen and CO2, basically switching over to something like SO2 and CO2?
Yeah, so I will say that that would be possible to do, with the caveat that you would be you would need an ECR3 flex to handle the SO2 due to chemical compatibility concerns. Otherwise, you'd damage your instrument and over time. But an ECR model of the 3 flex should be perfectly capable of handling SO2. Otherwise, like an ASAP or TriStar, I would not recommend it.
For all of your materials, you showed the really strong selectivity of ethane over methane. Can you discuss a little bit why ethane is so favored over methane in these materials?
Yeah, so I haven't. So the kind of the main goal of this research was kind of to go ahead and kind of just analyze very similar materials as kind of like the initial IAST study. Since this is kind of like the first time that this has really been integrated within our software, you know, I kind of wanted to start with kind of like the initial Myers and Prausnitz test, which was kind of looking at these 3 components of the methane, ethane, and CO2. They're also like very, very easy gases to acquire, and also gases of particular interest, particularly CO2 and methane, probably being you know, some of the most studied gases. CO2 for carbon capture and methane for natural gas. So that's kind of why I chose those materials. And then regarding the different carbons, the reason I chose those is because, you know, carbons, particularly kind of like these microporous carbons, are some of the original materials that have been studied. Carbons have been studied, you know, for a very, very long time, and kind of the initial Myers and Prausnitz research was looking at these carbon materials. These are obviously not the same ones that they use, but I kind of wanted to start from there. So in terms of why ethane is favored over methane adsorption, so, you know, there's not going to be any issue with diffusion limitations into these carbons, as they do have large enough pore sizes to accommodate both methane and ethane. Their pore sizes are more similar, in line with kind of like the ethane pore size, which is why overall they kind of favor that, almost acting as sort of like a sponge in terms of being able to more favorably interact with the ethane over methane, as well as CO2, since, you know, these are you know, microporous carbons. There's no sort of like metals or metal sites that would necessarily strongly or favorably bind CO2, which is why they're favorable for adsorption of ethane over both those over both methane and carbon dioxide, which are both significantly smaller than ethane.
Can you discuss briefly how you perform these breakthrough tests in the BTA, and then as well as basically some comments on, you know, you use mixtures, and how well are they controlled via MFCs in these devices?
Yeah, so how I conduct the studies is obviously I just for sake of time, I couldn't go through and do, every single mixture or, a massive number of mixture blends of like methane and ethane or any of the binary components. And that's kind of one of the main advantages of IAST is that, just by collecting 2 isotherms, I can predict what the selectivity will be at various different mole fractions. Whereas to experimentally do those, get those results, I would need to collect a very large number of breakthrough curves, at each of those separate concentrations. So more or less, that's kind of why I targeted the 50-50 mixtures. Of the 2 was just to kind of get that midway point. In terms of how those are controlled, so flowing, typically what I will do is activate the materials under nitrogen gas flow and at elevated temperatures, and then switch to a mixed feed of the ethane, methane, and a little bit of argon. And the main purpose of the argon is to act as like a tracer gas. So when argon should be a non-absorbing species. So when I first see that spike in the argon concentration, I know that's kind of like the start time for my integration for my breakthrough curves. And then from there, I'm able to integrate both the methane and ethane as an example, breakthrough curves to get the quantity absorbed. And yeah, that's kind of how, that's more or less how I conducted the experiment in terms of controlling flow rates. So the instrument is equipped with high precision mass flow controllers, allowing me to flow at a pretty broad range of flow rates. And then to go alongside that, there's also blending valves. So more or less what I can do is I can start my gas flow rates, ensure that they're sufficiently stabilized, and then I just engage my blending valves, which allows me to kind of tune in the particular mixture concentration that I'm really trying to target. So I have pretty accurate control over the flow rates of the components, and then the mixing is handled by the proprietary blending valves that are in the BTA.
The next question really kind of a deeper questions related to modeling and IAST and versus, do any of these models that are typically used for IAST have any considerations for the texture, the geometry of the surface? Are there any other considerations that would be built into these types of models?
Yeah, so to answer that question, so the models are kind of like the more or less the standard kind of like absorption isothermal models for predicting the gas absorption. So they take into account a variety of criteria depending on the model. Each model is going to have a little bit different set of criteria in terms of how that particular how it predicts a particular gas species to absorb to the surface of the material. So an easy example is, the Langmuir model is a one-to-one site. There's one particular binding site on the adsorbent molecule, one particular binding site on the material. Dual site Langmuir, it's exactly what you'd think. There's two different, the molecule binds to two separate sites on the surface of the material, and there's two separate adsorption sites to go with the two sites on the actual molecule where it absorbs. In terms of like the geometry of the surface, I don't know if you're referring to like a pore geometry or what exactly you mean by geometry, but this isn't the models here are not quite what you might think of based on like DFT models, which are kind of like elsewhere in their software. So it's a little bit different in terms of the models for the IAST are really looking at the isotherms in terms of how it absorbs versus like a pore shape, like a DFT model. So it's a little bit different in terms of the models that are there versus the DFT models.
Thank you. In a similar style to the earlier questions on SO2 and CO2, could you use ammonia for these types of analyses in either BTA or 3-flex for collecting pure component isotherms or mixture type data?
Yeah, so really ammonia or like any corrosive gases. So I talked about how, with your 3-flex, if you're looking to do IAST predictions for SO2, you'd want the ECR model. It'd be exactly the same for ammonia. You would want that ECR model, otherwise you would pretty quickly destroy some of the components in the 3-flex. But we have several customers that are using SO2 with the ECR 3-flex model, and they've been using it for years and had no problems. And that's exactly the same with like the BTA. So we do have a ECR model that is available. You would want to use it for ammonia, and the same thing for SO2. I guess the one thing that I would point out, it's even more important to have that ECR for something like a breakthrough, since you are going to be using gas flows, and you have more potential issues for exposure to humidity in kind of a flow-through system as what you might have in like an isotherm, where you can pump down to ultra-low vacuums and ensure that there's no water vapor in there. Whereas in a flow-through system, it's a little bit easier to get water in, so that makes it so that the ECR model is much more important. And you would need to couple, if you're looking at analyzing any sort of corrosive gas such as ammonia in your breakthrough, that you'd want to make sure that not only is your breakthrough ECR, but whatever your outlet detector is, whether it's a mass spectrometer or like an individual sensor or something like that, that you would want that to be chemically compatible in ECR as well. And I know that they do make both sensors and mass spectrometers that are kind of more enhanced corrosion resistant.
To clear things up a little bit for the audience, there's a question on 3-flex versus BTA. What gases did you use in the 3-flex? Were they pure component or mixtures versus what was used in the BTA?
Yeah, so for the 3-flex, the 3-flex cannot analyze mixed gases. So it uses it's a volumetric technique. And you can't distinguish between two separate gases in a volumetric system. So it's purely in the 3-flex was pure component isotherms. So I'm using like high purity methane, high purity CO2, and then high purity ethane. For the breakthrough, I'm starting with those pure gases. So I didn't buy like a mixed gas tank of like a 50-50 mixture of ethane, methane. I'm starting with those pure gases, but then in the system itself can actually mix the gases for conducting the breakthrough curves. So if you were to conduct like a similar study using whatever gases you're interested in, on your 3-flex, you need to use those pure gases, and then you could hook those same pure gases up to like a breakthrough system and then blend your gases in the appropriate concentrations that you're interested in to collect your breakthrough curves. So you wouldn't need to buy like separate gas cylinders, but it is, you do need those pure component gases to analyze on the 3-flex. It cannot handle mixed gases. Would be very nice, to get, and we certainly get this question relatively frequently, but there is no really great, there is no off-the-shelf system that can analyze these mixed gases and collect multi-component isotherms in a static setting. So that's why I choose to use Breakthrough for the comparison, is because we do have an off-the-shelf Breakthrough system which can do multi-component testing. However, it is flow-through instead of collecting static isotherms.
During your BTA portion of the presentation, you had a really strong comment about that you didn't observe any pressure drop during the breakthrough testing. What would you look for in a BTA curve to give you an indication there was a problem with pressure drop?
Yeah, so typically you wouldn't see, or it's harder to identify pressure drop from the actual breakthrough curve. When I was mentioning that, within the software there are pressure sensors and pressure controllers within the device. So all I meant is that throughout all these experiments, everything was designed to be run at ambient pressure, and in all of those experiments, I never saw the pressure rise above or below that ambient pressure, such that I can infer that there was no pressure drop during those experiments. Sometimes you may see that if there is pressure drop, oftentimes what that can lead to is very prolonged dead times. So you might introduce your argon gas, and maybe you're expecting that argon from the time you introduce it to the time you see it in your mass spectrometer to be like, somewhere around 10 or 20 seconds. If you have some pressure drop, what could happen is that argon could end up getting essentially stuck in the column for a much longer period of time. That's typically how you'd see it in the breakthrough curves, is, if you're running roughly the same sample quantity over and over again, and you have the same total flow rate, you should see roughly the same dead time in your breakthrough curves for your argon, and that's really just the delay from between, when you flip those blending valves on and you're mixing all of your gases to when you actually measure it in your detector. It takes some time for the gas to flow through there, and that's really what the dead time is in breakthrough. Oftentimes, if you have pressure drop, what you're going to see is your dead time is going to get expanded out significantly, because there is something impeding the flow of even your non-absorbing argon gas. So that's typically how you'd see pressure drop in breakthrough curves. In terms of in the actual system, you'd see it by a changing in the pressure, either up or down, depending on where your pressure sensor is in the device.
Next question is really related back to materials. Where you use powders during this study. Could someone perform a similar study, pure component absorption in the 3-flex with fibers, and then use that data with IAST rather than powders?
Yeah, so the materials I use aren't powders. They're little beads. They're very small beads. But they are very uniform in size. If you've ever purchased any of the superalkyl carbons, they're not a powder, but they're very tiny beads. But you could use beads, larger, significantly larger ones than the size that I've used. You could use fibers. There's a lot of different material types that you could use. You could use monoliths. So really, just about any kind of configuration of material, whether it's a powder, formed material like beads, you could use monoliths. So there's a very broad range of materials that you could analyze both in the 3-flex as well as in the BTA to conduct similar studies. So if your material's not a powder or not a bead, you certainly could conduct similar studies using it most likely in both 3-flex and the BTA.
A real practical software question. Someone inquires about updating older versions of 3-flex software to include IAST. Specifically for them, can you comment on what software version you used for all of your work?
Yeah, so I use the most recent version of the 3Flex software, which if you go onto our main website, and there'll be a tab that says support. Underneath that, under software, there'll be a tab that says software download. And the first hit on that web page is the 3Flex version 6.02, and that's the version I used for my IAST predictions, and you can download it. You could download it right now from onto any computer. And then if you scroll down, and that's where all of our instrument software is, the most recent versions. So yeah, you can just freely download that. If you go to our main website, click on the support tab, and then under software download, and you'll see the 3Flex will be the first download link underneath there.
So during your talk, you in answering questions, you specifically referred to the 3Flex for the pure component isotherms. Can you use data from any of the other instruments, perhaps an ASAP 2020 or TriStar or others? Can you use that data for your IAST predictions?
Yes, so you could use that data as well. So any of our instruments, you could use that data and open it in MicroActive version 6.0 or newer. And then if you don't have access to MicroActive, the other option could be is you can manually enter like isothermal data into like 3Flex software, but both of those would be available. So you're not limited to the 3Flex. You could any file that you can open in MicroActive, you'd be able to analyze for IAST, which covers both ASAP, TriStar. I don't imagine there'd be many people that would have a Gemini data for kind of multi-component mixtures, but in theory, you could use that as well and open it using MicroActive.
For your BTA work and the 50-50 mixture, did you use the BTA for blending the gases, or did you buy a bottled mixture?
Yeah, so I use the BTA to blend the gases instead of using a bottled mixture. But that's certainly something that you could do, and kind of the main advantage of using pure gases over a bottled mixture is you have more control over you can set it to whatever concentrations you want. So I did 50-50 just for simplicity's sake, but I could have done 25-75 of either component, or done like 90-10. There's a lot of flexibility there.
Can you perform similar types of work using vapors rather than fixed gases?
Yeah, so if you were interested in looking at predicting multi-component adsorption of vapors, that's something that you could look at as well. I will say that if you are interested in analyzing vapors, I would imagine that you would probably find that the IAST predictions are not very accurate. The main reason why I would expect that is just due to the if you're looking at water and like CO2 as an example, those are very chemically different species, and I would not expect the predictions to be very accurate. But it is certainly something that you could do, and then likewise with the breakthrough, that's something that you could do as well. As you could analyze water with any other species or multiple species if you were interested in that.
Yeah. For your study, you used all these microporous carbons. Are there any limitations? Could mesoporous materials be used?
Yeah, so if you were interested in analyzing mesoporous materials or you could use those as well. There's no reason you couldn't use micro mesoporous materials, pretty much any solid material.
Are there any limitations with respect to binary gas compositions and IAST predictions?
Yeah, so I will say that, with this initial release, it is limited to those binary mixtures. So certainly if you wanted to do like a tertiary mixture of like methane, ethane, and CO2, that hasn't quite been implemented yet within the software for doing ternary mixtures. You could do that ternary mixture or even add in more components in a breakthrough analyzer. But in terms of like limitations with the binary mixtures, so pretty much every gas that's within our kind of standard database should work within like the standard 3-flex database. And I believe that, that's somewhere in the realm of like 60, and I think, we have even more components in-house. So my guess is there's probably over 100 different species that you could analyze and predict different binary adsorption. And I haven't done the math, so I don't know how many different combinations there would be, but it would be a very large number. 100 different species. I don't know how many binary combinations that is, but that would be a lot. So, yeah, there are obviously some limitations. Anything that we don't have all the necessary property files for analyzing in something like a 3-flex, you wouldn't be able to use those gases. But there are in the 100 plus species that you could potentially predict binary adsorption mixtures for.
Again, back to your material selection, carbons, which aligns really nicely with a lot of the original work by Myers and Prausnitz. How difficult or easy can you do similar types of work with MOFs?
Yeah, so you could do the exact same study or kind of add on to that with metal organic frameworks. You're not limited in the types of materials that you're looking to analyze. So certainly you could do MOFs, microporous or mesoporous.
We're getting close to our time limit for this morning, so this will be the final question. There were a tremendous number of questions. Thank you, everyone, for participating. Julian, early on in your talk, you immediately said that you were expecting to see some differences for the CO2 studies when comparing IAST versus breakthrough analyses. Can you briefly comment on what you think the source of the differences would be when we look at results, experimental results from the BTA versus predictions that we saw from IAST, and possibly a few specific reasons why CO2 IAST data doesn't compare as favorably with BTA as the other systems?
Yeah, so I will say that overall I was quite happy with the observing similar general trends. Essentially the general trend of what I saw in IAST kind of matched with what I saw in the breakthrough system. In terms of like the absolute values, like in some cases they were much closer. They were very close in terms of the selectivities, and then in other cases, there were pretty significant differences. I think the biggest kind of discrepancy that I really saw is that in IAST, my ethane to methane selectivity was in general quite a bit higher than it was in my in some of the actual results. And then there was one sample where it was kind of flipped the other way around, where I had significantly stronger methane adsorption over methane than what I predicted. So it was actually, and I think a lot of that probably has to do with the fact that you know, it's never going to be perfect because we're kind of comparing, you know, two separate techniques. I mean, ideally, I'd be able to compare, you know, these static adsorption IAST predictions to isotherm predictions in a multi-component system. But kind of, as I highlighted in my talk, that instrument doesn't really exist, at least commercially. It's a multi-component static adsorption system doesn't exist. So when you add the effects of flow, you know, I didn't really see significant, you know, pressure drop or mass transfer limitations, which is what I would expect since these carbons are very uniform in size and, you know, they have large enough pore sizes that I wouldn't expect there to be mass transfer limitations. And then in terms of sizing, you know, they are very fine kind of particulates, but they're not like a powdered material. So overall, I would say that I was pretty happy with the general predictions, and that being able to compare kind of like on a one-to-one basis, you know, I'm doing a different style of technique, and it would be very difficult. I would not expect the results to completely correlate due to the fact that in one case, you know, as I said before, it's a static isotherm, and the other case, it's like a flow-through system. So I would not expect perfect correlation for that region. So having that direct comparison, it's hard to necessarily say because I'm not comparing like one-to-one.
Thank you. That's all the questions we have time for today. If we haven't been able to get to your question, one of our application team will be in touch shortly. Julian, is there anything else you'd like to mention today?
Yeah, I'd like to thank everyone for attending my presentation and getting a lot of great questions. And I'd like to you know, recommend everyone to do go ahead and download, you know, that newest version of our software on our website, and then you'll have access to these IAST predictions on your own. I'm very interested to hopefully see a lot of good work that's published in the literature that comes out of this new technique that we have available in our software. So thank you, everyone.
Great. Thank you, everyone, for participating in today's webinar. If you have any feedback for us, we'd be grateful if you could complete the survey, which will be distributed in a follow-up email. We hope you found the session beneficial. Do not forget to check back for upcoming webinars on micromeritics.com/webinars. We hope to welcome you again soon. Thank you.